okay, we are back again. So, before moving to that, your eigenvalue analysis, participation factor, right. So, all dynamic performances. So, before that, just a little bit of one or two small example, and that and if we want to convert the unit in English unit, that is British units, right. So, little bit of calculation of inertia h from W r square in English units we call, right. So, sometimes the moment of inertia of the rotor is given in terms of W r square, which is equal to the weight of the rotating parts multiplied by the square of your what you call radius of gyration in lb, that is pound feet square, right. Now, then the moment of inertia in slug into feet square is equal to W r square by 32.2, that is the value of g, right. The following relationship between MKS unit and English unit is useful in converting W r square to J, that is moment of inertia. For example, 1 meter is equal to 3.281 feet, right, and 1 kg is equal to 2.205 pound lb, that is mass, that is equal to 0.0685, that is kg, right. So, your sorry, your what you call is that is 0, your what you call 0.068 slug, sorry, not kg, this is actually slug, right. So, now 1 slug into feet square is equal to 1 upon 0.0685 into 3.281 square, that is equal to 1.356 kg meter square, right. So, English unit to your MKS unit, right. Sometimes we convert this. So, in this case, now the moment of inertia J in kg per meter square is related to W r square as follows. Therefore, J is equal to W r square upon 32.2 into 1.356, right. Therefore, we know that this equation number, right, I cannot recall this equation number, this one we have derived that in the swing equation h is equal to 5.48 into 10 to the minus 9 into j into rpm square by MVA rating. I cannot I have forgot to write the equation number, but you just find out that in swing equation this derivation is there. If I try to find out here, it will take time, but this has been derived for h, right. So, before we have done it, and we have done one or two small example also. Now, in this case what will happen, that your h is equal to that 5.48 into 10 to the minus 9 into 1.356 and j is equal to w 1.356 W r square by 32.2. Here we have made it j is equal to W r square by 32.2 into 1.356. So, with 1.356 W r square by 32.2 and rest is RPM square by MVA rating, it is there. So, if you simplify, h will be 2.31 into 10 to the minus 10 W r square into RPM square divided by MVA rating, that is megawatt second per MVA, right. So, take one small example. If the W r, here I have not written example number, if the W r square of the rotor including the turbine rotor of the 555 MVA generating unit is your 66,54,158 pound feet square, compute the following, right. It is given, that therefore, you have to calculate moment of inertia J in kg meter square, inertia constant h is megawatt second upon MVA, that is basically second, right, because megawatt upon MVA is a dimensionless. So, h unit is second. Stored energy, that is megawatt second at your rated speed, and now last one the mechanical starting time, right. Now, we know that j is equal to W r square upon 32.2 into 1.356, this just we have derived. So, W r square is given 654,158, it is given into 1.356 upon 32.2. So, this comes actually j is equal to 27,547.8 kg meter square, right. Now, part B, inertia constant, we know this formula H is equal to 5.48 into 10 to the minus 9 J into RPM square upon MVA rating, right. So, 5.48 into 10 to the power minus 9, then J we have got 27,547.8. So, 27,547.8 and RPM revolution per minute, that is 3,600, is 60 hertz you have considered, 60 hertz, right. If it is a 50 hertz, then it will be 3000, it is 60 hertz divided by 555. H is equal to then 3.525 second or megawatt second per MVA, but you can write second also, right. Now, third part is stored energy at rated speed. You know H into MVA rating. So, H is equal to 3.525 we got and MVA rating was 555. So, it will be 1956.4 megawatt second, right. And D, the mechanical starting time, we know Tm is equal to 2H. Earlier we have made this one, no, earlier we have seen it when we are doing swing equation. There we have seen Tm is equal to 2H, that is 2 into 3.525, that is Tm is equal to 7.05 second, right. This is the answer. Now, another example we have taken. The following are the parameters in per unit, right, in per unit and machine, on machine rating of the 555 MVA, 0.9 power factor, 24 kV turbine generator considered in example 2. 0.9 power factor means lagging, right. So, following parameters also are available in that example, but rewritten here. LADU is equal to 1.66 per unit, LFD is equal to 0.165 per unit, LAQU is equal to 1.61 per unit and RFD is equal to 0.0006 per unit and LL is equal to 0.15 per unit and RA is equal to 0.003 per unit, right. So, now first part is the field current, that is part A, field current required to generate rated started voltage ET on the air gap air gap line current. It is air gap line current I have missed it here, is it is air gap line current is 1300 ampere and the corresponding field voltage is 92.95 volt, right. So, what you have to determine, determine the base value of EFD and IFD in the non-reciprocal per unit system and the base value of EFD and IFD in the reciprocal per unit system. The reciprocal and non-reciprocal in the beginning of the course, the per unit system, everything is derived in detail, right. So, I got this example, I thought we should try to solve it here, very simple one, right. Now, part B is the compute the per unit values of EFD and IFD when the generator is delivering rated MVA at rated power factor and terminal voltage, right, these two. So, solution. By definition, the base values of EFD and IFD are respectively equal to the field voltage and field current, right. So, earlier when you are going for deriving that per unit system, just open those things once, right, because it was done in the early beginning of this course. To produce your relay rated air gap line voltage, hence that EFD base actually you can take 92.95 volt, this was given, and IFD base is 1300 ampere. Now, we know that IFD base is equal to LADU into IFD base, right, because that in per unit system, that your inductance and your reactance, they are same in per unit, I told you. That is why instead of writing in terms of X, I have written LADU into IFD base, so understandable. Therefore, IFD base will be 1.66, which this data are given, right, this data are given, that 1.66 and this is 1300, right. So, IFD base will be 2100 your 58 ampere, right. So, next is we also know that EFD base is LADU upon RFD into EFD base. Again I suggest you go back to this part when we are trying to base quantities, there you see this, right. That is why I have written, we know that, right. So, EFD base is equal to LADU upon RFD into EFD base. So, LADU is 1.66 and RFD is 0.0006 into EFD base is 92.95 volt. Therefore, EFD base is equal to 257.2 kV, right. Now, part B, from the results of example 2 at the rated output conditions, that example 2 you go back whatever you have done, that EFD we got 0.003939 per unit and IFD we got 1.565 per unit, right. The corresponding per unit values of EFD and IFD are that EFD is equal to LADU upon RFD into EFD. Therefore, EFD is equal to 1.66 upon 0.0006 into 0.009339. This EFD value, this we got from example 2, right. Therefore, it is coming 2.598 per unit. Similarly, IFD is equal to LADU into IFD. So, IFD is equal to 1.66 into 1.565. So, this is actually IFD is equal to 2.598 per unit. So, EFD and IFD in terms of per unit for this case it is coming same, right. I thought this one or two small example I should give you just for the purpose of understanding, right. So, next we will go to the next topic. Just hold on. Next, now we will come to the eigen properties of the state matrix, that is first will be eigen values and then slowly and slowly we will see that your what you call that your participation factor, right, and dynamic responses, right. So, the eigen values that you know, eigen values other things you have studied, right. So, the eigen values of a matrix are given by the values of the scalar parameter lambda. Actually my habit has become to write lambda like this. Actually it is like this, right. Actually lambda is like this, right, but my habit has become lambda like this. So you should forgive me for that, right. So, now question is that the lambda for which there exists non-trivial solution, that is other than phi is equal to 0 to the equation. That means, if you have matrix A, then A phi is equal to say lambda phi is equation 1. A is equal to your this you know n into n matrix, right, and phi actually n into 1 vector, right. So, now to find the eigenvalues of equation 1, that you know, that may be written in the form that A minus lambda I bracket close phi into phi is equal to 0. This is equation 2, this you know, right. So, next we will go to this next page, just hold on, right. Now, for a non-trivial solution, determinant of A minus lambda is equal to 0. This is actually equation 3, right. This is no need for you, this is for my reference, right. So, expansion of the determinant actually gives the characteristic equation, this you also know. The n solutions of lambda is equal to lambda 1, lambda 2 up to lambda n are the eigenvalues of A, right. So, if A is real, then complex eigenvalues always occur in conjugate pairs. One thing is there, if A is real and symmetric, then all eigenvalues are real, right. Just repeat, I am repeating, if A is real and your symmetric matrix, right, then all eigenvalues are real. But if it is not symmetric, then eigenvalues may be real, may be complex conjugate or both, right. So, complex eigenvalues always occur in conjugate pairs, that also you know, but in this case matrix A will never become your symmetric matrix, like your Aij not is equal to Aj for all cases, right. So, eigenvalues of another thing is that eigenvalues of A and A transpose are same, right. So, this you know. Next we need both right eigenvector as well as left eigenvector. So, first eigenvectors, for any eigenvalue lambda I, the n column vector, that is phi I, which satisfies equation 1 is called the right eigenvector of A associated with the eigenvalue lambda I. I just repeat, this you know it, but for any eigenvalue lambda I, the n column vector phi I which satisfies equation 1, that is we have given, is actually is has been written twice, right. So, it should not be there, one is here, right, is called the right eigenvector of A associated with the eigenvalue lambda I. Therefore, we have A phi I is equal to lambda I phi I for I is equal to 1 to n. This is equation 4. This is for my reference, right. So, the eigenvector phi I, it has the form like this, right. Phi I is equal to phi 1 I, that is phi 2 I up to phi n I. Since equation 2 is homogeneous, right, therefore, k phi I, where k is a scalar, is also a solution, right. So, thus the eigenvectors are determined only to, here also twice I have written within, forget about this. Thus, the eigenvectors are determined only to within a scalar multiplier, right. Similarly, the just hold on. Similarly, the n row vector, your what you call psi I, which satisfies psi I into A is equal to lambda I psi I, right. For I is equal to 1 to n, this right, this is do not see it, it is equation 5. This is for my own reference, it is called the left eigenvector associated with the eigenvalues lambda I, right. Now, the left and right eigenvectors corresponding to the different eigenvalues are corresponding to different eigenvalues are orthogonal. In other words, if lambda I not is equal to say lambda j, then psi j phi I is equal to 0. This is equation 6, right. So, this is, you forget it, right. I believe you have a little bit of knowledge on linear control system. So, only these are the preliminary things, because the left and right eigenvectors corresponding to the different eigenvalues are orthogonal. That is, in other words, if lambda I not equal to lambda j, psi j phi I is equal to say 0. This is equation 6, right. So, however, in the case of eigenvectors corresponding to the same eigenvalue, we can write that psi I phi I is equal to C I, where C I is a non-zero constant, right. This is equation 7, right. Since eigenvectors are determined only to within a scalar multiplier, it is common practice to normalize this vector, so that psi I phi I is equal to 1, or in other general psi phi is equal to I, the identity matrix, that we will see later. So, if you normalize this thing, so psi I phi I is equal to 1, this is equation 8, right, and these things are for my reference, this is not for you, this is 7, this is 8, right. So, psi I phi I is equal to 1, right. So, these are the preliminary things before entering into that eigenvalue analysis. Now, modal matrices. In order to express the eigen properties of a succinctly, it is convenient to introduce the following matrices. For example, phi is equal to phi 1, phi 2, phi n, this is equation 9. This is actually not a vector, right, it is a matrix. Later you will see this. This is not for you, this is equation 9, and psi is equal to psi 1 transpose, we have taken psi 2 transpose, psi n transpose and whole transpose, right. This is transpose, transpose, transpose and whole, this is equation 10, right. So, it is introduced the, this is actually matrix, these are all column vector, right, it is a matrix, and D is equal to a diagonal matrix with the eigenvalue lambda 1, lambda 2, lambda n as diagonal elements, right. That means, your D is equal to just hold on, that means D is equal to, actually it is a diagonal matrix, lambda 1, lambda 2 up to lambda n, other elements are 0, right, and this phi 1, phi 2, phi n or psi 1 transpose, psi 2 transpose up to psi n transpose, these are all column vector, these are actually total, it is a matrix, it is a matrix, phi psi, later we will see it is a matrix, but we are representing like this, right. Each of the above matrices is n into nth order, right. Your your matrix order A is n into n, so this is also n into n, diagonal D also n into n, because you have all n diagonal your what you call elements, that is nothing but the eigenvalues. In terms of these matrices, equation 4 and 8 may be expanded as follows. So, equation you can write A phi is equal to your phi d, equation 4 and 8, right. If you go back to equation 8, this condition is satisfied, psi phi is equal to 1, and if you come to your equation 4, right, here it is equation 4, that A phi is equal to lambda phi, in general A phi is equal to lambda phi, right, and that is A I phi I is equal to your lambda I phi I. So, it is written that A phi I is equal to lambda I phi I, that phi, or what you call A phi I is equal to lambda I phi I is written, but just let me explain here, that it is written here in equation 4 that your A phi I is equal to lambda I phi I. In general, A phi is equal to, we are writing phi d, because D is a diagonal matrix, that is it is phi, it is all diagonal elements are eigenvalues lambda. So, we can write A phi is equal to phi d, that is why you are writing here in this equation that your A phi is equal to phi d, this is equation 11, right. And we have seen psi I phi I is equal to 1, this is not for you, right. So, for my own reference, so psi phi is equal to identity matrix, or psi is equal to phi inverse, right. So, now this equation both side, this equation both side you multiply by phi inverse. If you multiply this by phi inverse and this side by phi inverse, so it is phi inverse A phi, it is here coming, and phi inverse phi is nothing but identity matrix, that is nothing but then it is D only, right. This is actually equation 13. So, phi inverse A phi is equal to nothing but the your D matrix, that is your diagonal matrix, or diagonal elements are your eigenvalues, right, of the matrix A, right. So, free now with this basic thing, now we will move slowly and slowly to the other thing, right, with this thing in our mind, because this thing will apply later. Now, free motion of a dynamic system, right. Now, free motion of a dynamic system, say with 0 input, can be given as delta x dot is equal to A delta x. This is free motion of a dynamic system. From that we will start, right. So, we can write that delta x dot is equal to A delta x. So, a set of equations of the above form derived from physical consideration is often not the best means of analytical studies of motion. The problem is that the rate of change of each state variable is a linear combination of all the state variable. The meaning is something like this. Suppose, for example, I am just writing somewhere this delta x. Suppose you have 3 state variable, right. For example, suppose delta x1, delta x2 and delta x3. Suppose you have 3 variable and A is a 3 into 3 matrix, right. So, that means let me we had it is a blue color. So, just hold on, let me change the your what you call that color, right, just hold on, right. So, it will be easy for me to put it, otherwise a blue color. Now, suppose you have a 3 state variable, then I am just overwriting on it, say then this is my delta x1 dot, delta x2 dot and delta x3 dot, right, and this side is A matrix, that is your A11, A12, A13, A21, A22, A23, say it is a full matrix, some other elements may be 0, A3 true and A33, and this side is your delta x1, delta x2 and delta x3, right. So, if you write delta x1 dot, say in this case delta x1 dot will be function of all delta x1, delta x2, delta x3. Some of the element may be 0, it does not matter, but delta x1 dot is equal to A11 delta x1, A12 delta x2, then A13 delta x3, like this. Delta x2 dot also your what you call A21 delta x1, A22 delta x2, A23 delta x3. Similarly, delta x3 dot also will be your A31 delta x1, A32 your delta x2, A33 delta x3. That means these state variables, they are so for example, this left hand side, that delta x 1 dot is also related to apart from delta x 1, it is also related to delta x 2 and delta x 3, right. So, that is why it is sometimes, that is why it is your what you call, it is not often the best means of analytical studies of motion. So, the problem is that the rate of change of each state variable is a linear combination of the state variable, that is delta x 1 dot, delta x 2 dot, like this, right. So, as the result of cross coupling between the state variables, consider a new state vector z related to the original state vector delta x by the transformation. So, what we will do? We consider a new state vector z, right. We do a new state vector z related to the original state vector delta x by the transformation. That is, we are assuming say delta x is equal to, so we are assuming phi into z. This is equation 15, right. So, we are assuming some new state vector. So, that means where phi is the modal matrix of A defined by equation 9, this we have seen earlier, substituting the above expression for delta x in the state equation 14. So, this equation here, your delta x dot is equal to A delta x, here you substitute this, right. So, if you substitute delta x is equal to phi z, that means my delta x dot will be phi z dot, right. So, it is phi z dot is equal to A phi z, because delta x is your delta x dot is equal to A x, and there you substitute delta x is equal to phi z. So, you will get phi into z dot is equal to A phi z, this is equation 16, right. Or this is not for you, or both side, if you multiply by phi inverse, so phi inverse phi is equal to identity matrix. So, left hand side it is z dot is equal to phi inverse A phi z, this is equation 17, but earlier we have seen that d is equal to phi inverse A phi, this is from equation 13, this we have seen, right. This is nothing but d is the diagonal matrix, right, that is all diagonal elements are the eigenvalues of the A matrix, right. So, that means we can write z dot is equal to dz. So, we can write z dot is equal to dz, this is equation 18, right. So, the important difference between equation 18 and 14 is that d is a diagonal matrix, whereas A is general is non-diagonal, right. That means what happened? D is a diagonal matrix, that means equation is lambda 1, lambda 2, lambda 3, lambda n, z 1 dot will become lambda 1 z 1, z 2 dot will become lambda 2 z 2, like this. So, other things are not involved, right. That means, this make your what you call analysis simpler, right. With this, thank you very much, we will be back.